Hey guys, welcome back. Another stream here today. I do have a goal of trying to do this a couple days in a row. This is now the third day where I've streamed. So yeah, going to be playing with the transistor circuit we looked at yesterday a little bit more. These really aren't saved. You can go to Twitter and see the old ones. I'm not going to really be publishing these on the YouTube channel, but if you go to my Twitter, you can check it out there. I also have been publishing over on the forum. So if you don't know, there's a forum for contextual electronics. If you have any questions, you can always ask here. I've been posting in this interested in streaming thread here, answering other questions. But people are doing build logs. If you don't know, there's also a course, and all of the course videos have an associated forum here, right? So basically, you know, if you click through to these, you may or may not be able. You'll be able to see the post, but you won't be able to. Hey guys, welcome back. Another stream here today. I do have a goal of trying to. There's the delay too. A little bit of inception. Anyways, this is the course itself. So, like I said, there's a associated forum post with each of the videos from the course, right? So this is the main site. Anyways, what we've been doing, and let me pull this up here, have been it always looks worse when you go back to it, right? What we've been doing here, though, is talking about just simple, basically a Class A amplifier, right? And kind of playing with the different values here. Normally what you do is you would be biasing, so usually over here, let me change a different color. So usually over here, what you would do is you'd have a signal source. You know, if you were in a normal scenario, you'd have a single signal source, you would capacitively couple it in, you'd have the rail, and then you'd have bias resistors here, right? And this is what normally happens, and then this would feed into here, right? This is what normally happens for a lot of, you know, for a simple Class A amplifier. But in our case, we are actually feeding this in with, we're just replicating this entire blue section with the signal generator, right? Because we have then control over the DC offset of the signal and the frequency of the output and stuff like that. So let's go take a look at what we're generating. This is going to be using the Analog Discovery 2, and well, actually, this is not what we're generating. This is what we're doing on board. Sorry. So simple transistor here, right? So up here, we're feeding the signal in here down through a collector resistor. There's an NPN transistor there. That's the 2N3904, and then there's an emitter resistor, and then we're also feeding in a signal over here on the base. We're also monitoring that signal. So we're monitoring. This is channel 1 here and channel 2 here. And so what we'll do is we'll go and look at this on the quote-unquote scope screen and see how we're doing here. Now, the reason that I wanted to stream today, and I'm streaming in the morning because I got stuff going on later tonight, but I wanted to stream today because I've been playing with some of these, with basically the generator, the signal generator here. And what I did is I went into, so if you go to custom, right, and then I wanted to kind of create a sweep. I saw there was a video from, oh crud, I'm going to forget his name. Who is it? No, not there. It was someone on YouTube. I added it to the subreddit for Reddit, or for the amp hour. Let's see the amp hour here. Oh yeah, here. So the Analog Discovery Curve Tracer. So this is Tom Tech Test was doing a curve tracer here. And so I was thinking about that, and then also because I was playing with some transistors here, I wanted to, you know, I was like, oh, well, that's kind of what we're doing. And I didn't want to do it. This is a very analog sweep here, right? But what I wanted to do is kind of show more of what we were dealing with yesterday. So basically, this is the signal that's on this is the signal that's getting injected into the base, right? So again, to go back, let me just play around with my screens a little bit more here. And I am trying to get better at playing with the screens. All right, so this is the signal that we were injecting into the base here yesterday. And if you saw that stream, you would have seen that I had this biased too high, right? I was up at I was up around 2.5 volts. Basically, it was like the signal. It was like this. Basically, it was like if this was 2.5 volts, right? The signal is kind of up here. And it's the DC value, right, that's going to, so this DC value here is going to basically determine the biasing between here and here, right, between base and emitter. And that's what actually turns on the base to emitter junction. It's also related to the fact that this is a 1K resistor, right? We're setting voltages instead of currents, and an NPN is a current device. However, because we have voltages here and we're not set, basically I was thinking about another thing that might want to do in the future is just create a current source that I control, right? So control the current source and then use that to actually sweep through different BE values, and then we can look at the current going through the collector emitter, right? Because that's effectively what a transistor, or sorry, an NPN transistor, how it works, right? There's from the base to the emitter, right? The current flowing from the base to the emitter. Let me go back to my drawing here. Sorry. So the current flowing from the base to the emitter is multiplied by the beta value, right? So usually about 100 or so, and then that represents the current gain that happens in the collector to emitter, right? And that gets down to the semiconductor physics stuff and probably more advanced than we need to get to here. But what we do as a proxy here, right? We set a voltage. We set a voltage on the base between the drop from the base to the emitter plus the resistor down here. That sets up a current. That small current then creates a larger current from the collector to the emitter. I'm not sure if you can see my mouse here. Probably cannot. Is this? No, that's a smudge. I don't know if there's a way to better view the cursor here. Sorry. So, if VBE is 0.1 milliamps, right, and our beta equals 100, then IBE, right? So the current flowing from the base to the emitter is 0.1 milliamps, and then the beta is 100, which is just kind of a standard off-the-shelf value that most you can assume for some transistors because you're never actually using it directly. Then ICE, right, current flowing from collector to emitter, assuming it's available, right? You have to assume that as well. Could be upwards of 10 milliamps, right? And then the idea being that we use that current gain to then amplify, well, a couple things, right? If we're doing an emitter follower, right, we might use this current going not to the scope but out to another circuit out here, right? You might use it to drive some additional stage, right? So you might drive some other stage over here. You might have a load resistor here, right? There could be a bunch of options there. If we're doing a not an emitter follower but a common emitter, right? That's when you pull the voltage off of here, and that's what we're kind of looking at here. You have a larger signal gain based on this resistor up here. This diagram is getting increasingly messy. So let's just go over to the bench and check that out again. So I'm going to go to right screen. So I did actually add in another view up here so you can see if I'm actually looking at this thing. What I'm also going to do is see if anyone's actually in the chat. I did not actually look for that. Let's see. Okay. Oh, hey, Sebastian. So, yes, Sebastian's watching. 10 people are watching. Wow. I love you guys. I'm really doing this for my own practice. I hope that's clear. But I wanted to get one in today, too. Okay, so let's... what do we want to do now? Okay, so what am I showing here? So I am showing... I can't tell... Yeah. You can see the whole screen, right? Yeah, you can see the whole screen. So what I'm doing is I'm setting up a sweep here. And this is a little bit weird because when you set up the sweep, so if you go into edit this function here, I actually went in and I actually just, so first I generated using values, but this wants to generate between minus 1 and 1. So what I did is I did between 0 and 1.5. You see there's a hop up to the 0.6 volt where the whole thing turns on. And I just wanted to see, so these are the actual values I wanted to see. Then I hit normalize, and then I had to go in and actually had to shift this whole thing down. And then when I actually implement it, I actually offset it by 500 millivolts. So anyways, the general output here is it goes 0, 0.6, 0.65, 0.7, 0.75, 0.8, and onwards up to 1.5 volts. And what we see here is basically, so this yellow one is the orange lead here, and that's actually looking at the just below the. This is backwards. Oh, sorry, let me just flip that around. I added that last night without quite getting it. Layout. You're going to see a flip here. There we go. Yeah, that's reality now. Yeah, that's better. Okay, sorry. Okay, so we're looking at the orange one correlates to this yellow one on screen, the yellow thing on screen. What the blue one represents is on the base of this NPN transistor, right? So this is the voltage we're actually applying here. And these are just DC values that are stepped up, right? You can see that this is going really slow, 3.24 seconds per division. I just slowed this thing way down. It's because, I'll show you in a second why I did that, but so basically I'm stepping through these different values, putting different DC voltages on the base, and then seeing what happens up here, right? And what we're basically doing is we're doing an IV curve for the whole thing here, right? So basically we're just turning on the transistor, and then we're watching what happens when we start to source current down through, this is a 10K up here, and then a 1K down here, right? So we're just looking at the amp, so it's not even the amplification, I guess it is being amplified, but you can see at the top here, when the transistor isn't turned on at all, what we see is that there's no current flowing through the resistor, so there's no drop here, right? So the 4.5 that's up at the top here, that is basically what the rail is set at, right? And I can move that up even. I could set that to 5 volts instead of 4.5. You'll see it move up on the next sampling. And so what we see, though, is basically the yellow represents how much current is flowing through here, right? So we see it would be when there's 5 volts, there's no current flowing. When there's point whatever this is, so 0.7, that looks a little bit low actually. That is a little bit low. Okay, so this is a little bit lower than I thought. This is starting at 0.3 volts or so. So right about here it starts to turn on, right? So 0.6, 0.7. The transistor, the VBE, is creating current on the in the base, from base to emitter, and then it's turning on current from C to E, and then what we're seeing is this voltage represents the drop in across this resistor here, right? We're just looking at it backwards. So if we wanted to, how could we do that differently? I guess if we did, yeah, how could we do that? I guess we could move it up and see it sweep in the other direction. But it's not a huge deal here, right? You'll probably see some, it's still sampling. It's taking forever to sample. And we could tell because it hasn't gone up to 5 yet. But anyways, so there's no current flowing here, right? And then the current starts to flow, and then it drops from, so then this represents whatever the voltage is here. So like that's, what, 4.5 down to 4 let's just say 4.4, so 0.1 volts, 0.1 volts divided by 10K, divided by, yeah, should be the current, right? So it's very low current. And that's how we could basically back calculate the current that's actually flowing through VCE. Now remember, the current that's flowing through VCE is effectively the same current that's flowing through, the current that's flowing through the collector should be effectively the same current that's flowing through the emitter. Now it's going to be a little bit higher because the base is contributing a little bit of current here, but not really that much, right? Now what happens here is, as the voltage goes up and up and up, it starts to it starts to equalize rather, because the current flowing from the source here, from the power rail here, starts to balance out with the current flowing from the base to the emitter, and really that's the effect that we saw yesterday. Okay, I'm not sure if that was clear at all, but we'll see. Let's also now, so the reason I really wanted to do this is, this still hasn't moved. Wow, that's going real slow, really slow. Okay, so the reason I really wanted to do this though is now let's change this thing up. So we're going to go over to, so now that I've set up a custom signal here, right? And that's cool. Now let's go to modulation. And what I'm doing now is basically I'm going to modulate the output. Oh, you see it just finally moved in there. But now what I'm going to do is actually modulate the output and zoom in quite a bit here. And now what this is effectively going to do is start showing the signal as basically a sine wave that gets added on top of the DC value, right? So the step is our carrier, and it looks like it's actually amplifying a little bit more based on percentage. I wish I could flatten this out. I don't know if there's a way to flatten this out. Yeah. So it is going to amplify a little bit. You see it at the end of the signal, it's amplifying a little bit more. But what we're effectively trying to do is add a small sine wave signal. And there it is. You can kind of see it there. What we're trying to do is basically step through all of these values now, all these DC values, and show how the amplification changes over time. Position. Let's go to 0 here. We're just going to normalize this thing to 0. Hopefully it'll start to resample. Yeah, and now what you see is these DC values starting to sneak up here. And as the transistor turns on, right, so now it's starting to turn on, now we actually see some of the amplification as it's happening, right? So now, and then it restarts again. So right, so we're going through, we're at 0, 0.3, 0.4, whatever. You see, this is the signal that's getting added onto the base, right? So this is the base signal that's happening, and you see that it actually looks like the same signal the whole time here. The thing that I don't understand is it looks like it's there's no offset. Okay, so if we set an offset here, so it's starting right about 0, and then it's creeping up to about 1 volt. So it's actually not, it's never overloading. Let's zoom in a little bit more. We should actually be able to see some of these sine values. And what we're really trying to show here is that as this DC the DC value, right? So as we change the bias, right? This DC value represents the bias from the base to the emitter. As that changes, you can actually see the amplification happening, right? What we're basically doing is we're readjusting the bias as we go. So I'm going to actually move this up a little bit here. Let's just move this up to 200 millivolts, give it a healthier starting point. So it'll go a little bit higher now. What we should see is now that it's going a little bit higher, right, we should actually see that it overloads now that it gets past the 1 volt mark, right? So it's going to actually, yep. So now it's going a little bit past, let's see now in this one, because it looks like it started a little bit lower last time. So you see the DC bias really isn't turning on that transistor at all. As it does start to get through, now it's turned on, right? What we're really seeing is now, we're still only going to 1 volt though. What does I want to do here? Let's take this up to 400 millivolts. I have to go through one more cycle here. Because if it goes past the 1 volt mark, right, what we'll start doing is basically running into the territory. Is it still moving? No, it's not going past there. That's weird. Let's try this one more time. If it does get past the 1 volt mark now, what we'll see is that it's going to start overloading basically. So this represents about the max amplification here. Yeah, okay, it is doing that. It's just the triggering's off. Okay, so let's see it one more time. And there's not really a way to pause this as far as I can tell. So you see right about at 900 millivolts, that's about our maximum amplification. Oh yeah, okay, so it was that. So as we keep going up past 1 volt, right, you see that the amplification starts to die off, and that's because the contribution of the current from the base to the emitter and the contribution of current from the collector to the emitter starts to normalize, and so we really lose that amplification factor. Once it goes past about 1 volt, it's not properly biased anymore, and that's what we're really getting at here. So if let's see, if I set my, I don't really know how to make it pause at the proper place. Yes, clear as mud, as Steven says. But what I'm trying to get at is that if we turn all this stuff off, right, if we go back just to simple, right, and we set the offset at 900 millivolts, we set the sine wave here, amplitude, that's good. That's actually a little bit overloaded. Oh, this amplitude's too high. So this is about the signal we were looking at last night, right? So the base signal is this 200 millivolt peak to peak sine wave, biased at 0.9 volts. Now the transistor is turned on at the probably the optimal value here, right? From here, right? So now, not there. So now from here, right, we're turning on the base to emitter at 900 millivolts DC value with a small sine wave on top of it. So that biases the transistor on properly. Then that small sine wave basically flowing down starts to draw current down through this. Let's give it one more color here. How about orange? So I really don't want to redraw the whole thing, so I'm just going to erase a bunch of stuff. A bunch of stuff. Let's see how much I can erase. Okay. So what we're seeing is basically this signal here, right? It's around 900 millivolts, right? We have a sine wave that's on that. And then what happens is once we open up the channel, so the VBE, this 900 millivolts plus this 1K resistor, so about 1 milliamp through here, it basically opens up the channel for VCE, and then that sine wave basically starts to draw current down through this resistor, right? And then the current, and it's drawing current in both directions, that right, drawing current in both directions, and that it's basically the sine wave is moving current back and forth across this resistor, and that's what we're seeing here at channel 1, right? So we're seeing channel 1, and then so in the output what we see is we see something somewhat centered around the 2 volt mark, 2 volts, and we see a larger signal here, and we see it basically, whereas this is 200 millivolts, this is 0.2 volts peak to peak, and this over here is 2 volts peak to peak. Wow. Still getting used to this drawing board. So then this is 2 volts. Yeah, there it goes. 2 volts. Okay. Whew. Okay, so and we saw that back over here. Okay. What we can also do here, since we've already got it in line, so what I'll do is I'll just take another, so what happens now is if we take a 10K resistor and we put it in line with this other 10K resistor, right? So that should drop the resistance by half, right? 2 10Ks in parallel is 5K. So now we should see that amplification drop, and there we do, right? So we see that this up. So now basically we kind of reset the drawing board, because now our 5-to-1 ratio, right? So 5K to 1K, all that math changes now. So what we really want to do is we would have to change the bias point. So we move that up a little bit. Now our overall amplification is going to change, right? We 1.1, right? 1.2. So really that's about, we'd want to bias it at about 1.2 here. But what we also see is that the amplification overall has changes. Now it's a 5-to-1 amplification instead of 10-to-1. Okay. So another stream, definitely trying to keep it short because my apartment's getting boiling. I'm sweating like crazy. If you have any questions, we do have a forum, and we'd love to talk to you over there. We do appreciate everyone hanging out and watching the stream. Where is it here? So if we go here, middle screen. If you don't know, there is a forum, and it is free, and we do have people participating, regardless of whether they're involved in the course or not. So you can ask any kind of question you might have. If you have a question, if you have a stream request, if you want to see some kind of topic, I'm probably going to run out of topics eventually here. Well, not really. Let's be honest. I've got lots of topics ready to go at any point. So we could start doing this stuff. I was thinking I'll just do some simple RC stuff too, because that's kind of fun to play with. We could probably do more stuff with the Analog Discovery 2. The reason I'm streaming in the first place is to play with more with this Analog Discovery 2. That's likely going to be a much bigger part of the course in the near future. And then also just to kind of, I don't know, brush up talking about electronics at the base level, and then also, you know, get people involved, and hopefully you're hanging out and enjoy this stuff. So, yeah. So if you got any questions, head over to the forum. Thanks for watching.